Metamathematics is the study of mathematics itself using mathematical methods. This study produces metatheories, which are mathematical theories about other mathematical theories. Emphasis on metamathematics is due to David Hilbert's attempt to prove the consistency of mathematical theories by proving a proposition about a theory itself, i.e. However, metamathematics provides a rigorous mathematical technique for investigating a great variety of foundation problems for mathematics and logic, among which the consistency problem is only one. History. Metamathematical metatheorems about mathematics itself were originally differentiated from ordinary mathematical theorems in the 19th century to focus on what was then called the foundational crisis of mathematics. Richard's paradox concerning certain definitions of real numbers in the English language is an example of the sort of contradictions that can easily occur if one fails to distinguish between mathematics and metamathematics. Something similar can be said around the well-known Russell's paradox. Metamathematics was intimately connected to mathematical logic, so that the early histories of the two fields during the late 19th and early 20th centuries largely overlap. More recently, mathematical logic has often included the study of new pure mathematics, such as set theory, recursion theory and pure model theory, which is not directly related to metamathematics. Serious metamathematical reflection began with the work of Gottlob Frege, especially his Begriffsschrift. David Hilbert was the first to invoke the term metamathematics with regularity. In his hands, it meant something akin to contemporary proof theory, in which finitary methods are used to study various axiomatized mathematical theorems. Other prominent figures in the field include Bertrand Russell, Thoralf Skolem, Emil Post, Alonzo Church, Stephen Kleene, Willard Quine, Paul Benes-Arif, Hilary Putnam, Gregory Chaitin, Alfred Tarski and Kurt Gödel. In particular, arguably the greatest achievement of metamathematics and the philosophy of mathematics to date is Gödel's Incompleteness Theorem, proof that given any finite number of axioms for Peano arithmetic, there will be true statements about that arithmetic that cannot be proved from those axioms. Today, metalogic and metamathematics are largely synonymous with each other, and both have been substantially subsumed by mathematical logic in academia. Milestones. The discovery of hyperbolic geometry. The discovery of hyperbolic geometry had important philosophical consequences for metamathematics. Before its discovery there was just one geometry in mathematics. Even the idea of another geometry was improbable. When Gauss had discovered it, it is said that he did not publish anything about hyperbolic geometry out of fear of the uproar of the Boeotians, which would ruin his status as Princeps Mathematicorum. The uproar of the Boeotians came and went, and gave an impetus to metamathematics and great improvements in mathematical rigor, analytical philosophy and logic. Begriffsschrift is a book on logic by Gottlob Frege, published in 1879, and the formal system set out in that book. Begriffsschrift is usually translated as concept writing or concept notation. The full title of the book identifies it as a formula language, modeled on that of arithmetic, of pure thought. Frege's motivation for developing his formal approach to logic resembled Leibniz's motivation for his calculus ratiocinator. Frege went on to employ his logical calculus in his research on the foundations of mathematics, carried out over the next quarter-century. Principia Mathematica, or PM, as it is often abbreviated, was an attempt to describe a set of axioms and inference rules in symbolic logic from which all mathematical truths could in principle be proven. As such, this ambitious project is of great importance in the history of mathematics and philosophy, being one of the foremost products of the belief that such an undertaking may be achievable. However, in 1931, Gödel's Incompleteness Theorem proved definitively that PM, and in fact any other attempt could never achieve this lofty goal, that is, for any set of axioms and inference rules proposed to encapsulate mathematics. There would in fact be some truths of mathematics which could not be deduced from them. One of the main inspirations and motivations for PM was the earlier work of Gottlob Frege on logic, which Russell discovered allowed for the construction of paradoxical sets. PM sought to avoid this problem by ruling out the unrestricted creation of arbitrary sets. This was achieved by replacing the notion of a general set with the notion of a hierarchy of sets of different types. A set of a certain type only allowed to contain sets of strictly lower types. Contemporary mathematics, however, avoids paradoxes such as Russell's in less unwieldy ways, such as the system of Zermelo-Fraenkel set theory. Gödel's completeness theorem. Gödel's completeness theorem is a fundamental theorem in mathematical logic that establishes a correspondence between semantic truth and syntactic provability in first-order logic. It makes a close link between model theory that deals with what is true in different models, and proof theory that studies what can be formally proven in particular formal systems. More formally, the completeness theorem says that if a formula is logically valid, then there is a finite deduction of the formula. It was first proved by Kurt Gödel in 1929. It was then simplified in 1947, when Leon Henkin observed in his PhD thesis that the hard part of the proof can be presented as the model existence theorem. Henkin's proof was simplified by Gisbert Hasenjager in 1953. Gödel's completeness theorem says that a deductive system of first-order predicate calculus is complete, in the sense that no additional inference rules are required to prove all the logically valid formulas. A converse to completeness is soundness, the fact that only logically valid formulas are provable in the deductive system. Together with soundness, this theorem implies that a formula is logically valid if and only if it is the conclusion of a formal deduction. Gödel's incompleteness theorem. Gödel's incompleteness theorems are two theorems of mathematical logic that establish inherent limitations of all but the most trivial axiomatic systems capable of doing arithmetic. The theorems, proven by Kurt Gödel in 1931, are important both in mathematical logic and in the philosophy of mathematics. The two results are widely, but not universally, interpreted as showing that Hilbert's program to find a complete and consistent set of axioms for all mathematics is impossible, giving a negative answer to Hilbert's second problem. The first incompleteness theorem states that no consistent system of axioms whose theorems can be listed by an effective procedure is capable of proving all truths about the relations of the natural numbers. For any such system, there will always be statements about the natural numbers that are true, but that are unprovable within the system. The second incompleteness theorem, an extension of the first, shows that such a system cannot demonstrate its own consistency. Tarski's definition of model theoretic satisfaction. The T-schema or truth schema is used to give an inductive definition of truth which lies at the heart of any realization of Alfred Tarski's semantic theory of truth. Some authors refer to it as the equivalent schema, a synonym introduced by Michael Dummett. The T-schema is often expressed in natural language, but it can be formalized in many sorted predicate logic or modal logic. Such a formalization is called a T-theory. T-theories form the basis of much fundamental work in philosophical logic, where they are applied in several important controversies in analytic philosophy. As expressed in semi-natural language, S is true if and only if S. Example: snow is white is true if and only if snow is white. The impossibility of the Entscheidungsproblem. The Entscheidungsproblem is a challenge posed by David Hilbert in 1928. The Entscheidungsproblem asks for an algorithm that takes as input a statement of a first-order logic and answers yes or no, according to whether the statement is universally valid, i.e., valid in every structure satisfying the axioms. By the completeness theorem of first-order logic, a statement is universally valid if and only if it can be deduced from the axioms. So the Entscheidungs problem can also be viewed as asking for an algorithm to decide whether a given statement is provable from the axioms using the rules of logic. In 1936, Alonzo Church and Alan Turing published independent papers showing that a general solution to the Entscheidungs problem is impossible, assuming that the intuitive notation of effectively calculable is captured by the functions computable by a Turing machine. This assumption is now known as the Church-Turing thesis.